Hello, everyone. Uh, we will start promptly today. We're going to continue working on chapter 4. Specifically, we're about to finish section 2.4. We have a little bit, one additional result, and then we'll start the one after that, okay? We're working on the last thing. So we saw last time, we consider the following series. So from last time, we checked that this series is convergent and this series diverges. But more importantly, something that is not in the book specifically, like I'm gonna say it right now, but I think it's important, is the following remark, right? So let me write it as a remark here. Remark. And it's the following. It's that if we have a series of positive terms, so if this one over here is a series where an is greater than or equal to 0 for all n, then the series converges if and only if, and that's why this is so cool, if and only if the sequence of partial sums is bounded. That's all we need to do to check. And why is this remark true? Well, on the one hand, if we know that the sequence of partial sums is bounded, because there's, okay, let's provide a little bit of an explanation. So, because the ANs are greater than 0, then the sequence SM of partial sums is increasing, right? Correct, because every time you're adding more things. So the partial sum is, so remember the partial sum is, let me write it here, is A1 plus A2 all the way to AM. So then one after that is going to have an additional term. So, and because the terms are positive, that term will make the partial sum a little bit bigger, or it may stay the same if you add 0, but it's going to be increasing according to our definition. So because it is increasing, then if it is bounded, then by the monotone convergence theorem, if in addition SM is bounded, then by the monotone convergence theorem, SM is convergent. Right? And if the partial sums are convergent, that's exactly the definition that the series is convergent. So that establishes one way. That says that if the partial sums are bounded, then it is convergent. But it also works the other way around, because if the partial sums are not bounded, if the partial sums grow without bound, then they don't have a limit. That means it goes to infinity, right? So similarly, or conversely, rather, conversely, if SM is not bounded, then the limit of SM is infinity, right? That's pretty much the definition, and which means the limit doesn't exist, i.e. the limit does not exist. Does not exist, so the series diverges. Okay, so I just wanted to write down this. I mean, it's mentioned in the book, obviously, but it's not written down like that, and it is important. That's the reason we're actually jumped, right? I mean, we were looking at limits of sequences, and this was a good moment to start talking a little bit about series, because we can say a lot about series, at least a series of positive terms, right? It turns out that all we need to check is if they're bounded, and that's fantastic. That's way easier, right, than anything else. Of course, just for the purpose of knowing if it's convergent or divergent. If you actually know what it converges to, that's an entire different story, right? And we will talk about that later on. But to finish off this section, we have this theorem. It's called Cauchy's condensation test. And we'll explain it a little bit and then later use it. Cauchy's condensation test. And it says the following: suppose Bn is a sequence that is decreasing, so the terms are becoming smaller, and Bn is greater than or equal to 0 for all n. So positive terms and decreasing. Okay, if you have one of those, then the series Bn from 1 to infinity converges if and only if, it's again a powerful theorem because it gives an equivalence conditions, if and only if the series and this is the condensed series, I'll show to you what it is 2 to the n b sub 2 to the n from 0 to infinity. What is this? Let's write the first few terms. Is the first one is 2 to the 0, so that will be 1 b sub 1. Then when n is 1, you get 2 b sub 2. Then you go to 4 b sub 4. And then 8 b sub 8, etc. Right? You get it? We're going by powers of 2. And we're multiplying the kth term by 2 to the k. So over here, you would have eventually 2 to the n, b sub 2 to the n, and then continue, right? So it's kind of like the series you would create if you decide to, what is it that we're doing? How can I explain it? Well, it's a little bit like the trick we did with the harmonic series. Remember where we were grouping by the first term, then the next 2, then the next 4, then the next 8, then the next 16. We're kind of like, we're essentially doing that, and then changing all of those terms, making them the same. So here are 4 terms that are the same, right? I mean, you could think of this, instead of the way it's written, you could think of this as B1, then 2 B2s, then 4 B4s, then 8 B8s, and so on, right? Maybe I'll write it here. So you could think of this as B1, then B2 plus B2, 2 of them, and then B4, 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 4 of them, and so on, right? So 4, then the next one would be 8, 8 of them, and then for the next one, 16, and so on. So in that way, it should relate to the way we did it for the harmonic series. Okay, and that's what it is. And as a matter of fact, we're only going to prove half of this if and only if, because the other half is given as a homework problem, right? In fact, the other half is the easier one, in my opinion. And you would essentially mimic what we did for the harmonic series. So here we're only going to prove half of it. So we're going to show that that this one, if this one converges, then that one converges, and you still need to show the other way that if. So okay, let me write proof. So there's 2 parts here. One of them would be to show that, I'll write it like this. This one, 2 to the n, b sub 2 to the n converges, implies that this one converges. And I'm being, I mean, I don't want to write all the details, right? I mean, under the general assumptions, and I didn't write from 1 to infinity. I'm just writing the implication. This is one of them. And the other one would be the backwards one, right? That if this one converges, then that one converges. And, and the way to prove the backwards one is instead to show the contrapositive. So to show this one, that this one converges, implies that the compressed one converges, the condensed one. Instead of doing this one, we do, you can do the contrapositive. The contrapositive is not this one implies not that one, right? If it's raining, there are clouds in the sky, and the equivalent statement is if there are no clouds in the sky, then it is not raining. So equivalently, if this one is not convergent, that means diverges, then the original one diverges. And that's your homework, right? So this one is what you are asked to show. It's exercise 2.4.9. So I'm not gonna do that one. I'm gonna do the first one, all right? So let's take a look at the first one. Let's continue the proof. So this part you're gonna do yourselves, and I'm gonna work on the first one, all right? So here we go. So suppose, let's write down our assumptions. So suppose that this series converges. What is the meaning of this? Well, the meaning of this is that the partial sums are convergent. So I'm gonna define the partial sums. So then, if we define, I'm gonna call them t's. So t sub k is going to be b1 plus 2b2 plus 4b4, etc. And we're gonna stop at 2 to the k, b sub 2 to the k. So in other words, is the partial sum. 2 to the n, b sub 2 to the n, from 0 to k, stopping at k, right? So then if we define these partial sums, what we know is that the limit exists. We know that the limit of the t case exists. Okay. Now, actually, I don't need to use the limit because of our previous remark, right? Really, the only thing I'm after is to show that my sequence of partial sums is bounded. That's enough. Remember, that was my first remark in today's class. All I need to do is to argue that the sequence of partial sums is bounded. Now, a good thing about a convergent sequence is that it's bounded. That was our first result about sequences. Remember that? So the fact that the limit exists means this sequence is bounded. So by an earlier result, we know that the sequence tk is bounded. Okay, thus what that means is that tk is less than or equal m for all k. Notice that I didn't put absolute value bars because this is a sequence of positive things, right? Okay, so what is it that we want to show? We want to show that not this series, but the regular series that only has bn is convergent. So for that, to show that, we need to show that the partial sums of that regular series are convergent. Okay, so let's write it here. We want to show that this series b sub n from 1 to infinity converges. It is enough to show that the sequence Sm is bounded, where Sm is what you think it is, b1 plus b2 all the way to bm, right? And this is enough because we know that this is a series of positive terms, so it's increasing, and then by the remark that we argued before, if it's increasing, meaning monotone and bounded, then by the monotone convergence theorem, the limit exists. So all we need to argue is, why is this sequence bounded? It's all we need to do, all right? And then it's not too bad to, it's not too hard to do it. I'll explain how we can do it. So here's how we can do it. So the only thing you need to do is to pick an appropriate K to relate these two, the SM with the TK, all right? And how do we do that? Well, here's how. Fix M and pick K large enough so that M is smaller than or equal 2 to the K plus 1 minus 1. And we can do that, right? Because 2 to the K becomes as big as you want, right? Powers of 2 can be made as big as any number you want. So you can find a power of 2 that is big enough to surpass M, or M plus 1 if you put the 1 on the other side, all right? And then all I need to show you is, so now we'll argue, we will argue that SM is in fact smaller than TK. And because TK is in turn smaller than M, and capital M, then that's going to be enough. We're going to show that the sequence of partial sums SM is bounded, i.e. SM is bounded by M. Okay, so that's all we are left to do. We need to argue why this inequality is true. And it's actually relatively easy to do that. I'll tell you why. Let's just write down what these are, right? So we're gonna follow the same idea. So here's why. So clearly, first thing is that because M is, because the sequence is increasing, this is smaller than if I just use this number instead, the 2 to the power K plus 1 minus 1. See, this is obviously true. And then I'm going to write down this one, right? What is S sub 2 to the power K plus 1 minus 1? What is that one? Well, that one is B1 plus B2 plus B3 all the way to this number, gigantic number, K plus 1 minus 1, right? And all I need to do now is group these guys accordingly. So I'm gonna now move over here as sub 2 to the K plus 1 minus 1, what that is, and I'm gonna group them like this. B1 by itself, then B2 and B3, then B4, B5, B6, and B7, so the next 4 terms. Then from B8 to B15, that's one less than B16. And then etc., right? So my last collection will be from 2 to the K to 1 less than the next power, which is precisely the last term, 2 to the K plus 1 minus 1, right? So that's, I just rewrote all of these terms and I'm dividing them, grouping them in a way that is useful, okay? Good. Now it's the moment where we need to use our assumptions. So we already used one of them, which is that all the terms are positive. Otherwise, we cannot use the monotone convergence theorem to simply show that boundedness will suffice. The other important assumption, if we go back to the statement of the theorem, let me put it right here on top. If we go back, is this one. We haven't used this at all. That the BNs are decreasing, that the BNs are getting smaller and smaller. We have to use this one, otherwise this result is false, okay? So this is now the moment where we're gonna do it. How? Well, we're gonna change this by the following. Here I'm gonna write B2 plus B2. And why is that true? Because B3 is bigger than B2. Smaller. I said it wrong, right? The b's are becoming smaller. So B3 has to be smaller than B2. Same thing here. So B5, B6, and B7 are all smaller than B4. So I can write B4, 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 and B4, 4 of them. Then all of these numbers here from 9 to 15 are smaller than B8. So this is less than or equal than B8 plus B8, etc., B8, and there's 8 of them, and so on. So this will be B sub 2k plus B sub 2 to the k, B sub 2 to the k, and there are exactly 2 to the k terms, right? And what is this? Well, this is exactly B1 plus 2B2 plus 4B4, etc., all the way to 2 to the k, B sub 2 to the k. That's exactly the definition of TK. Look, let me just slide over right here, definition of TK. That's exactly what it is. So this guy is TK. Let me go back to where we were. This is TK. And that's it, right? Because we wanted to find that inequality, right? This inequality over here, that SM is less than or equal to TK. So we are done because SM is smaller than this one, and this one is smaller than TK. And because this one is bounded, we are done, right? So this is the end of the proof. All right. So it's a nice result, and you'll come to appreciate it when we apply it, right? And I'm going to, this is the part that probably the only little criticism. I like our book a lot. I think it's written very terse and straight to the point in a concise way. But here, I thought that they could have presented the geometric series and then use this to show the P series right away, and instead they do it later. So we're going to actually do things in a little bit of a different order than the book, just tiny things. Don't worry about it, but I think that will give more justice to this result. Okay, so that's it, and let me move to the next section, and then we'll come back using this result later on. All right, but we need a little bit of extra things because before we can use it to its full strength. So here's the next section. The next section is called subsequences, and the Bolzano-Weierstrass theorem. Okay, so we'll start by right away defining what we mean by a subsequence. All right, so this is important. Here's definition. If you have a sequence, an arbitrary sequence of real numbers, and you let n1 less than n2 less than n3, etc., be an increasing sequence of natural numbers. And if you do all that, then this new sequence, a sub n sub 1, a n sub 2, a n sub 3, etc., is called a subsequence. It's a new term we're learning, of an. And it is denoted a sub n sub k. All right. Let's see some examples. Best way to understand the concept. And more importantly, non-examples, right? Things that are not subsequence. So a little remark here. You don't get to rearrange the order. That's important. So remark, the order of the terms in the subsequence is the same as the original sequence. So no rearranging, okay? Let me explain. Here's an example. So imagine that our AN sequence is our old friend 1 over n. So that one is 1, 1/2, 1/3, 1/4, etc. 1 over n, and you keep going, right? That one. Okay. So this one is, here are some subsequences. So then this one is a subsequence. If you go 1/2, 1/4, 1/6, 1/8, 1/10, that's a subsequence, right? What are we doing here? We're taking some of the terms only, right? But keeping the order. So we're taking the second term and the fourth and the sixth and the eighth. So we're only taking the even terms. So that one is a subsequence. Then this one is a subsequence. Here's another one. What if you go 1/10, 1 over 100, 1 over 1000, 1 over 10,000, etc. That works too, right? Now we're skipping way more, but that's okay. That's a subsequence. I'm taking the 10th term, then the 100th term, then the 1000th, then the 10,000 term, etc. I'm going by powers of 10, right? So this one is also a subsequence. But here are ones that are not, all right? Here are non-examples. So these are good, but if you pick this one, 1/10, 1/5, 1 over 100, 1 over 50, this one is not. Why is it not? Well, because they don't go in this order, right? I mean, these elements appear in the original sequence. That's correct. They're all reciprocals, but you have to keep the order, right? If you pick 1/10, then the next one has to be bigger. And here you pick 1/5 as the one after that. So you went forward, and then now you're going backwards. No backwards, okay? You have to pick things that are still going forward, right? Increasing. The sub-indices must be going in an increasing way. So this is not a subsequence. This one is also fails. So if you pick something like this, 1, 1, 1/3, 1/3, 1/5, 1/5, this is also not a subsequence, right? Because after 1, there's not another 1, right? There's only 1, 1. So this would be like you stay there, right? So here, it's strictly increasing, right? You need to pick one that is strictly to the right of the previous one. Okay? Is that clear? What we mean by a subsequence? And they are important. They will be extremely helpful whenever we want to find out the limits of sequences, because of the following first little result we're going to see. So this is kind of like something that you know already and you think is probably obvious, but it requires a proof. And this is what it says, theorem 2.5.2. And what it says is that subsequences of a convergent sequence converge to the same limit as the original sequence. So if you get subsequences, then those subsequences should be convergent to the same answer. So Andronic asked on the chat, is it true that subsequences are never finite? Yes, subsequences by definition are infinite, same as the original sequence, right? Yes. So in other words, subsequences are sequences themselves, and we define sequences to be infinite, right? There are functions from the natural numbers to the reals. So you have to use all the natural numbers. Mm-hmm.
Professor, so if you were to stop somewhere in the
then
sequence,
we don't call it a sequence, right?
okay.
It's just a list of numbers, a finite list of numbers. Mm-hmm. Well, what if your sequence has an alternating order? Yeah, if your original sequence has an alternating order, then it's okay to for you to preserve that one, right? So if your original sequence alternates, goes back and forth, then as long as your subsequence, so the important thing in the subsequence is that you have to pick them, so you pick one of these, and then one further to the right, and then another one further to the right, and so on. So if the original one had been something that goes up and down, then maybe the subsequence also goes up and down. But to be a subsequence, you need to pick things that are further to the right. Okay, is that clear, Alexander? Okay, so to illustrate the theorem we're about to prove, see this sequence that we had here converges to 0, right? Obviously, the 1 over n numbers are getting smaller and smaller. And look how these two subsequences also converge to 0, right? This one is getting, the numbers are getting smaller and smaller, and the same thing happens in here, right? Numbers are getting smaller. So that's the property we are preserving according to this theorem. So let's write down the proof. It will be an easy proof, you'll see. Proof, well, let's see, assume or suppose, assume that the sequence an approaches some limit a. And let an sub k be a subsequence of an. Okay, then we're gonna write down what is the meaning of these. We're using the definition. So given epsilon greater than 0, we know that there is some n in the natural numbers such that if n is bigger than capital N, then an and a are within epsilon. All right. And all we need to do is show a similar property with the sequence an sub k. And it's actually easy to do this. The same capital N will work, as a matter of fact. Observe. So note that if little k is bigger than capital N, then since n sub k is bigger than k, right? I mean, why is this true? Well, because remember, it's a subsequence. So you have to pick the kth term in the subsequence. So the kth term in the subsequence means you're picking k of them, and maybe you skipped a bunch of them, right? So in the worst case scenario, you didn't skip anything, and you picked the kth term of the original sequence. If it's not the worst case, then you're even further to the right, okay? So this happens, and k is bigger than k, but k is bigger than n. It follows that nk is bigger than k, which is bigger than n. In particular, nk is bigger than n. That's the one I really want, because then I can use the previous one. Thus, ank minus a is less than epsilon, right? And that's it. So given an epsilon, whatever epsilon you want, I found a capital N. It happened to match with the capital N of the original limit. We were lucky. And using that capital N of the original limit, I know that if little k is bigger than capital N, then the kth term in the subsequence is within epsilon of a. So I'm just going to write here as our punchline, that is the limit of a and k is a. So if we have a subsequence, it converges to the same thing. All right, that's what we learned right here. Okay, and now here's the first example of this. This example already helps us out to get some very specific limits, which we're now gonna go and use with our previous result with the Cauchy's condensation theorem. So this is example 2.5.3, I believe. Okay, so we're going to look at this sequence. We're going to pick some constant number between 0 and 1. By the way, the case between -1 and 0 is one of your homework problems, okay? And then what we want to show, that the limit of b to the n, when n goes to infinity, if you want, let me write it so that it's super clear, is 0. Okay? How are we going to do it? Or here's how. Because 0 is less than b less than 1, if I multiply this inequality by b, because b is positive, the inequality is preserved, right? So because b is greater than 0, multiplying b less than 1 by b gives b squared less than b. And if I do it again, then in turn, if I again multiply by b, what I get is that b cubed is less than b squared, and b to the fourth is less than b cubed, etc. Right? So in general, this is what we get. We get that b is bigger than b squared, which is bigger than b cubed, which is bigger than b to the fourth, etc. Right? In other words, our sequence b to the n, what happened here? My exponents became subindices. B squared, b cubed, b to the fourth, b to the n. All right, now it's correct. So our sequence b to the n is decreasing, right? It's going down. So it's monotone. And it's obviously bounded, right? Because all of them are positive. So it's bounded by 0 and it's decreasing. It's always between b and 0. So we already established one important thing, right? The limit exists. So let's just write it here. This means b to the n is monotone decreasing. And it is also bounded by 0. Great. So we have a sequence that is monotone and bounded. Great. So then by the monotone convergence theorem, the limit exists. Then by the monotone convergence theorem, the limit of b to the n equals L exists. So the limit exists. That's half the battle, right? The second part of the battle is find out what it is. What is that limit? We wanted it to be 0. How can we prove it is indeed 0? And now this is where we're going to use a subsequence, right? So let's consider a subsequence. Consider the subsequence b squared, only the even powers. So b squared, b to the fourth, b to the sixth, in general, b to the n. So it's the sequence b to the 2n, right? So that sequence has to be also convergent by the previous theorem, right? Because it's a subsequence of the original one. So this one also converges, and therefore it must have the same limit. So by the previous theorem, the limit of b to the 2n is also equal to L, right? But now we're going to use some of the properties of limits we proved. This limit of b to the 2 to the n, we can do it in a different way. So by the algebraic limit theorem, we know that if we want to do the limit of b to the 2n, well, that's the same as the limit of b to the n times b to the n, right? And we learned that the limit of a product is the product of the limits. That's the algebraic limit theorem. So this is in fact the limit of bn times the limit of bm. Right here. Limit of Bn, right? The limit of a product is the product of the limits. But this one is L, and this one is L, so this is L squared, and the original one was L, right? So, now we got a clue of what L has to satisfy. L has to be equal to L squared, right? Thus, L equals L squared, or L times L minus 1 is equals 0. So we have two choices. Either L is 0 or L is 1. All I need to do to finish up the proof is to show that L is not equal to 1, right? How do I check that L is not equal to 1? Well, we're going to use another of our limit theorems, the order limit theorem, right? Because let's go back. Our sequence is always less than b, right? Our sequence is less than or equal b. So note that, let's write it here. Note that b to the n is less than or equal b for all n. So then if, so this inequality is preserved when you take the limits. Thus, the limit of b to the n is less than or equal the limit of b. But that's just, limit of b is just b, that's a constant function. And limit of b to the n is L. Let's just give it a little bit of space here. So L is less than or equal to b, but b is less than 1. So L is less than 1. That means it's not equal to 1. Hence, L is not equal to 1. And then if it's not a 1, the only other possibility is 0. Yeah. And that's it. Really cool example, right? I mean, it's in a very indirect way, we were able to find out what the limit of this expression is. The limit has to be 0. And we proved it essentially by using this subsequence and eliminating the other possibility of it being 1, right? So it's not going to be 1. That's fantastic. So let me, we can now go back to another example that we had. I don't know if you remember. Let me mention it here. So this is another example we had before, one that we left pending. We had this sequence, this one, you may remember. It was 1, 1/2, 1/3, 1/4, 1/5, then negative 1/5, then 1/5, then negative 1/5, then 1/5, then negative 1/5, etc. Remember that one? And so it keeps alternating negative 1/5 and 1/5. So now we can show that this one is divergent, that this sequence has no limit. So we can now show this sequence is divergent. Why? Well, let's suppose not. Let's suppose it is convergent. Suppose not, i.e. that the limit of this sequence, let's call this sequence something, let's call it S, A, B, A, let's call it A, AN, i.e. the limit of Ln is some L, right? Let's suppose it has a limit. All right, so then I'm gonna pick the following subsequences. I'm gonna pick the following subsequence. The sequence where the first term is this guy, 1/5, and then the one after that is this one, and then this one, and then I keep going like that, right? So in other words, I'm picking the sequence. Consider the sequence, the subsequence. The subsequence, what is this one? 1, 2, 3, 4, 5. A5 is the first, then A7, then A9, then A11, etc. Right? We consider that subsequence. Because the original sequence converges to L, then this one should be convergent to L as well. So this one should be convergent to L. All right.
Professor.
Yes.
But I thought you had to choose, like, wherever you start, you have to just go from there.
Yeah.
For it to be a subsequence.
Yes.
So then,
didn't I do that? I started here. 5, and then you pick anything bigger than this one. I'm picking this one. This 2 to the right.
Oh, I thought you had to just go from like 1/5 and then -1/5. Like I thought you had to go from then on.
No, you get to skip, right? You get to jump however many ones you want, right? Like look at the previous one we did this one. Here we didn't pick, we're skipping one every time, right? We started b squared, then b to the 4th, so we skipped b3, and then b to the 6th, we skipped b to the 5, right? So
Okay.
a subsequence means you get to pick some of them, but you have to pick them in order, right? It's not okay to rearrange them.
Okay.
Yeah, I'm glad you asked, because yeah, that's probably the hardest part about all of these, is to actually understand what is a subsequence. That's the hardest.
Professor?
Yes.
One more question.
Yeah.
So I also, to my understanding, I thought the subsequence also had to be increasing.
Increasing in the sense that you need to pick further, the indices are increasing, like here. So 5, 7, 9, you need to move to the right. The numbers themselves, they can go up and down. We don't know. That's a little bit like Andronic asked. No, Alexander, I meant.
So based off of this example, according to our remark, where the one you picked, where an is equal to 1/n, and then one of the examples you said that is not a subsequence, you did 1, 1, 1/3, 1/3, 1/5, 1/5. Is that because you did like A1, A1, A3,
Correct.
A3?
Exactly.
Okay.
Very good. Exactly. Yeah. So here I picked A1 and then A1 again. That's not good. You need to increase, right? Go a little bit further. Yeah.
Okay. Thank you.
Yes. No problem. Again, glad you asked. Always ask your questions, guys. I'd rather that you're following me, or otherwise I'm talking to my screen. Where were we? Okay, so we're trying to show that this has no limit. And the way we're going to do it is, again, in an indirect way, showing that we would get two different things. And I already showed you one sequence, this one, but we already know that this sequence is actually made up of numbers that are all 1/5, right? These are all 1/5. So if this was true, that this sequence converges to L, then L would need to be 1/5, right? So from here, it was the implication would be that L equals 1/5. And then, of course, by then, some of you have realized that I can play the same game, but this time I'm gonna use these other ones. This time I'm gonna start here and use all these other ones, and then I'm gonna get a different answer. So, however, the subsequence, this time I'm picking 1, 2, 3, 4, 5, the 6th term, and then going by evens. Would also be convergent to L, but this one is all made up of -1/5. So if they're all -1/5, then this would mean that the limit is -1/5. And that cannot be, right? The limit is unique. You cannot get two different limits. So this is a contradiction. And the contradiction means that this sequence has no limit, right? So this sequence is divergent. Thus, the sequence is divergent. Remember, divergent means it's not convergent, right? It's just a fancy name to say not convergent. All right? Okay, so now we are going to this is the part where we're gonna skip a little bit ahead. This is briefly mentioned in 2.7, but it's not. I don't know why they didn't do it here. It's the part that I was telling you that this is actually where it fits. And so we're going to talk a little bit about geometric series. You know them already. In fact, this is something that we actually explain quite well in our regular classes. We do explain where they come from and why they add up to what they add, etc. So this part, most of you know already, and you probably learn it the right way. So what is a geometric series? It's a series that looks like this: a r to the n, from 0 to infinity, right? And then what do we know about these guys? Well, we know that they are convergent if R is between 0 and 1 in absolute value, right? And we even know what the sum is. So let's talk about all of that. And I'm only going to do it this time around where the R is between 0 and 1. So suppose that 0 is less than R is less than 1. So we're going to pick an R between 0 and 1. And then these are easy to analyze because the partial sums are easy to analyze, right? What we use is the following. If you multiply 1 minus R times 1 plus R squared all the way to R to the power m minus 1, like so, what you get is a telescopic sum, right? I mean, let's do the product. When you multiply 1 times all of these, you get this. I'll rewrite it here. And then when you multiply negative R times these guys, you get negative R squared, negative R cubed, negative R to the m minus 1. And the last that you get is negative R times R to the m minus 1. That's R to the m. And I even wrote them like this, one on top of the other in the way they match. So you can see that all of these terms cancel. That's why we call it telescopic, right? So the answer is 1 minus R to the m. And it's a very common telescopic sum. So then, and this is very useful because then that means we can do the partial sum, right? The partial sum of this series. So thus, if you do the partial sum, what is that partial sum? Is A plus AR squared all the way to ARM minus 1. So I factor the A, and what I get is 1 plus R plus all the way to R to the m minus 1. And if I just use what we learned, I can replace this one by 1 minus R to the m divided by 1 minus R, like so. Right? So that is what this partial sum is. And then remember, because R is between 0 and 1, we can use the previous example we learned. So what would be the limit of the SM? Well, the limit of the SM would be the limit of the expression we just figured out, which is A times 1 minus R to the m divided by 1 minus R, right? And now here by the algebraic limit theorem, this A is a constant and 1 minus R is a constant. We can then take them out. And then all you need to do is the limit of 1 minus R to the m. Then again, by the algebraic limit theorem, you can break this limit as the difference of the two limits. So this is A over 1 minus R times the limit of 1 minus the limit of R to the m, right? And then this one is obviously 1. It's a constant function. It's just a constant sequence, 1, 1, 1, 1, 1, 1, 1, forever 1. So of course the answer is 1. And this one is the one we just learned. See, I changed you the letter. The letter used to be B. This time we're calling it R. But we know R is between 0 and 1. So therefore this guy is actually 0. So we got it, right? Then the partial sums have a limit. And this is the answer, right? So then this guy is convergent. So thus, a geometric series converges if 0 less than R less than 1, and the value of the series is actually A over 1 minus R, right? That's the one you probably knew very well from calculus. Okay, awesome. So now I didn't do the case when R is between -1 and 0, but we're gonna find out. So I'll just put a little note here. there's a homework problem from homework. The limit of b to the n is also 0 if b is between -1 and 0. So this also happens if you pick a number between -1 and 0. So then the same proof would work if r is between -1 and 0. And it also works for 0, right? But if you pick 0, that's just 0, 0, 0, 0, 0, 0. So from homework, this is true. So in fact, the series a to r to the n from 0 to infinity equals a over 1 minus r for absolute value of r less than 1. So it works for an arbitrary r between -1 and 1, excluding -1 and 1. All right? And that's how you can check those geometric series. All right? Now, we're going to leave pending what if r is bigger than 1? And in that case, it's divergent, but we're going to do that later. All right? So we're not doing totally geometric series just yet, because we need to establish what happens when the r is bigger than 1. But you knew this already. You probably learned it and did even this multiplication and everything, did the partial sums in your calculus class. I know I do it, and I know at least a few of you took calculus from me. So at least for those of you, I'm sure. All right, but now we're going to use these for to do the p-series test. All right, so what is the p-series test? So p-series. The p-series are like the ones we did one of them. We did 1 over n squared. So these ones are a bit more general. They look like this: 1 over n to the p, where p is a number greater than 0. Okay. All right. So for numbers that are greater than 0, we know that this 1 over n to the p is a decreasing sequence, right? You get numbers that are smaller and smaller and smaller. So we can now use the Cauchy's condensation theorem. All right, that's what we want to use. So let's write it here. So let's apply. So first, note that the sequence 1 over n to the p is decreasing. Right? You're dividing by numbers that are bigger and bigger, right? P is fixed. So even if P is like 1/2, right? Square root. If it was 1 over square root of n, you would be doing 1 over square root of 1, 1 over square root of 2, square root of 3, square root of 4. So those numbers are, in the denominator, are bigger. Therefore, you're going down, right? So it is decreasing. So because it is decreasing and positive, we can use Cauchy's condensation theorem. So by Cauchy's condensation theorem, what happens? Well, this one is convergent. Converges if and only if the other one converges. Remember what's the other one, the condensed one? It was like this. It's 2 to the k times b sub 2 to the k, right? So you need to do the 2 to the k term. And the 2 to the k term would be 2 to the k to the power p. From 0 to infinity converges. So this one will be convergent if and only if this one converges. And here's the good thing about this, that this one we can do, right? This one, even though this looks harder, this one we can actually do, all right? Let's take a look at it. What is this new one? Is 2 to the k times 1 over 2 to the k to the p from 0 to infinity. Rules of the exponents tell me that I multiply these two, k and p, so it's now kp. And then again, rules of the exponents tell me that I can write this as the exponent 2 to the power k minus kp, right? Further, I can factor the k. So it's 2 to the k times 1 minus p, right? And then I can write it in this form, which is my preferred form, because now it looks like a geometric series, right? This is some number, 2 to the 1 minus p, raised to the power k. And we go from 0 to infinity. That's a geometric series. Geometric series. With what is our r? With our r is 2 to the 1 minus p, right? That's our r. So then how do we know if this one is convergent? Well, we just figured it out, right? It's convergent. That's the part that we did before. Let me scroll down. If we scroll down over here, we said that this series is convergent if r is between 0 and 1. All right, so that's all we need to do. I mean, it's already positive, this number. So this will be convergent. Convergent if r is less than 1. And what does that mean? It means 2 to the 1 minus p is less than 1, right? And then if you multiply by 2 to the p both sides, this means 2 less than 2 to the p. And this number is bigger than 2 if and only if p is bigger than 1. And that's the p-series test, if you remember it, right? So we know that the 1 over n to the p, this one, is convergent if and only if p is bigger than 1. If the exponent is greater than 1, it's convergent. So when p equals 1, it is not convergent. That's the harmonic series. Remember, that was divergent. If you pick anything that is less than 1, like 1/2, that's also divergent. But if you pick 2 or 3 or 4, all of them are convergent, right? And this time we could do it. And like I mentioned last class, we did it without using the integral test or anything that uses integration, right? We did it in a straightforward way, right? The new result was Cauchy's condensation theorem. That was the key player in this proof, right? Cauchy's condensation theorem is what made it work. All right, well, and the fact that we know geometric series. If we don't know geometric series, then it would be hard for us to do this one. All right, so this is the little part that I was telling you that it's actually in 2.7, you know, doing the p-series test. In fact, the book mentions it. So the book has the p-series test in 2.4, but then it says that you're going to do it in exercise 2.7.5. So I essentially did exercise 2.7.5 right here. All right, excellent. So we have about 10 minutes to go today, and I at least want to, it's okay that we're falling a little bit behind versus my schedule because, well, we already did a little bit of something that is on a later section anyways. So let's get started with this theorem. And this one is the one that had the name, the big name. So it's theorem 2.5.5. And this one has a name, is the Bolzano-Weierstrass theorem. And I'm thinking maybe if we have the time, we'll get to talk a little bit. So this class is awesome for you math majors to also learn a little bit about the history of mathematics. So we mentioned already one main player, Cauchy. That's Augustin Louis Cauchy, French mathematician in the 1700s. Awesome. He did so many things. And here you find a couple of others, right? Bolzano and Weierstrass. It has a hyphen because it was sort of discovered independently by each one of them. Weierstrass, German, and Bolzano, an Italian mathematician. All right. So, but yeah, maybe we'll learn a little bit about history of mathematics. I'll provide a few slides or something that you can take a look at. Okay, so here's what it says. It says every bounded sequence, it is a beauty. Every bounded sequence contains a convergent subsequence. That's fantastic, right? So you can always find, even if I try to give you a very chaotic sequence that goes all over the place, you can always find a subsequence that is convergent, as long as it's bounded, right? And the bounded part is necessary. I hope you can see that. If you find something that is not bounded, then obviously it's gonna grow really, really big, either to infinity or to negative infinity. And if it grows a lot, it may not have a convergent subsequence, because perhaps everything grows along with it, right? So let's just put a little bit of an observation here about that. So remark, the bounded hypothesis is necessary. E.g., take a look at the sequence n, the sequence 1, 2, 3, 4, 5, etc. No matter what subsequence you pick, it's going to go to infinity, right? Every subsequence is unbounded and thus has no limit. Diverges. Right? So that's this bounded part is necessary. But once you have the bounded part, then it's awesome. You can find a convergent subsequence. Isn't that something, right? Okay. And this is a beautiful proof. You, in a certain sense, sort of say where how you can find that subsequence in a very simple way. So I'm not going to write down the proof thoroughly today, because we have, maybe we could, but we will be rushing through it. What I'm going to do is I'm going to give you the idea. What is the idea for this proof, right? So proof idea. And what I'm going to do is draw some diagrams, which is an even better way of explaining the proof, right? I'm just going to draw some pictures here. So here's a real line. And remember, we have a bounded sequence, right? So bounded means everything fits between negative m and m for some m, right? So let's put those numbers there, negative m and m. So the entire sequence you can find in here, in this part over here, all right? And then here is the idea of a proof. So we have a sequence. I don't know where the sequence is, right? It's somewhere over here. So let me put a few of them here. So maybe A1 is here, and then maybe A2 over here, A3, A4, then maybe A5 jumps here, maybe A6 is close to A1, then A7. I don't know what the other guys do, right? I don't know. They are all over the place, or maybe they start getting close to 0, some of them. I don't know. I don't know. It's a sequence like this, right? We don't know much about it. It's an arbitrary sequence. All we know is that it is between negative n and m so far, okay? So here's the idea, how we're gonna try to find the subsequence, okay? Here's how. And it's a very simple idea. I'm always surprised by how easy is this idea. What we're gonna do is we're gonna divide this into two pieces. So think of this, and two equal pieces actually. So think of the interval from negative m to 0, and the interval from 0 to m, right? Those two intervals. And then you're gonna ask yourself the following question. Which of these two pieces has the most elements of the sequence, right? Which one of the two pieces has more of the a's? Now, I'm being not very precise here, because you can say more. What do you mean more, Professor? Maybe there's infinitely many here and also infinitely many here. And yes, you would be right. So here is what I want to do. I want to argue that one of these two pieces, one of the two pieces has an infinite number of elements of the sequence. one of the two pieces has infinitely many. That has to be true, right? Why is that true? Well, imagine that doesn't happen. Imagine that over here there are only finitely many, right?
And it would be a finite.
Exactly, right? If there's only finitely many here and finitely many here, then altogether it's only finitely many. And then that means it's not a sequence, right? It's something, it's a list of numbers that stops somewhere along the way. So one of these two has to be infinite, right? And without loss of generality, let's suppose it was the right one. Suppose this one was the big one. This one was infinite. Then what do you think we're gonna do? Well, if something works, you do it again, right? And then again and again and again. So then the next step in the proof would be to divide this guy into two pieces. And ask yourself again, can we argue that one of these two pieces is infinite? And the answer will be yes, because if both were finite, then the original one would be finite, but we pick an infinite one. So one of these two pieces has to be infinite. Maybe now is the right one. Maybe now this one is the infinite. And then what do we do after that? We do it again, right? We divide this guy in two, and one of these two has to be infinite. Maybe now is this one. And then we do it again and again and again and again. And okay, and have 1 minute. So I'm gonna tell you, we're gonna keep doing that. And then at some point I have to pick the subsequence, right? And picking the subsequence is gonna be super easy. All we're going to do is we're gonna pick an arbitrary one. So in the first one, in the orange one, I'm gonna pick one element, whichever one I find in here. Maybe A1, this guy. Then when I'm over here, I'm gonna pick one element in the green part, whichever is in the green part, maybe this guy. Then I'm gonna pick whichever one is in the purple one, this one. And then this process continues, right? We're halving, halving, halving. And at every step, I'm gonna pick an element. There are infinitely many, so I can pick one. That's not an issue, right? You can always pick one. And that's gonna be my subsequence. Okay, now the only thing that I need to do is to show you that that subsequence converges. And we need to do something additional there. And that's where we're gonna pick it up next time, all right? We're gonna properly write the proof of this Bolzano-Weierstrass theorem, and that would be the end of section 2.5. All right, I don't wanna keep you, take more of your time. It's already a long class as it is. All right, so I'm gonna stop right here.